Hello! Today, we are going to be talking about propensity score matching, the most widely used method in applied causal inference. Let's get hands-on with a no-code tool, walk through a case study, and learn the theoretical background. In a nutshell, propensity score matching is a technique used to create a virtual randomized controlled trial. So first, let's have a quick refresher on what a randomized controlled trial is. Imagine your platform has a vast number of users. Each person is a unique and diverse individual.
There are enthusiastic users, users who have only registered, elderly users, and they differ in gender and nationality.
However, if you randomly select users from this population and divide them into two groups, as long as you have a certain sample size, characteristics of these two groups will become remarkably similar. Their average age, gender ratio, app access frequency, and so on. The characteristics of these two groups will become remarkably similar in every aspect. In this case, we say the two groups are homogeneous. First, let's try this out. For this demonstration, I've prepared sample data for 5,000 users, including their age, height, weight, weekly training, and leg muscle. Let's actually check the data. It consists of a wide range of ages from their teens to their 70s and includes many diverse people in terms of height, weight, and so on. As explained earlier, from this data, I will create two groups by random sampling. We use the Node Builder widget to perform data transformation. By describing the desired transformation in text, the AI automatically generates a workflow. Here, we requested random sampling and random assignment into two groups, A and B. If the AI's proposal looks good, click Build Transform Nodes. All right, a new column group has been created. Visualizing the distribution, the age distribution seems almost identical between Group A and Group B. The blue curve represents Group A, the red curve represents Group B, and the two curves completely overlap. This indicates that the two groups are homogeneous, and height, weight, etc. are also perfectly matched. Just in case, let's perform a statistical test with the A-B test widget. The results of the t-test are displayed in the main area on the right. There is no statistically significant difference in age between Group A and Group B. And we can see that the p-values for other variables are also large, indicating no significant differences. It has been proven that creating two groups by random sampling makes them homogeneous. Now, we have two homogeneous groups. Suppose we change the app's UI for only one of these groups, and the access frequency increases. We can then infer that this change was caused by the new UI. Since the only difference between the two groups is the new UI, there can be no other reason for the lift in access frequency. This is the fundamental concept behind an RCT. First, we create two homogeneous groups. Next, we give some kind of treatment only to one of them. After observing for a while, if a change occurs in that group, you can identify the effect of the treatment as a direct causal relationship. This concept can be applied to various things. For example, by giving a new drug to only one group and comparing, you can determine the drug's effect. By providing new education to only one group and comparing, you can measure the impact of a new educational method. Or even test if new shoes help you run faster. This idea was conceived by Ronald A. Fisher, the father of modern statistics, and it has become a cornerstone of modern science. Let's go over some common terminology. The intervention applied to only one group is called treatment, and the group that receives the treatment is called the treatment group. The group that does not receive the treatment is the control group, and the result that is expected to change as a consequence is called the outcome. Before we move on to PSM, let's look at an incorrect use of an RCT. A sports brand has released new special shoes. They are very expensive, but they claim that wearing these shoes will make you run faster. Your son is begging you to buy them. According to this brand, of two groups, they had only one group wear these special shoes and conducted an experiment to measure their 100-meter dash times. They claimed that the treatment group had better times. By chance, you were able to talk to the people who participated in this experiment. It turns out, looking at the details, that there was a difference in the average age of the two groups. The control group consisted of boys around 10 years old, while the treatment group was made up of young men around 20 years old. From this result, can we conclude that the shoes make you run faster? The answer is no. The reason is clear. The difference in physical ability due to age is considered a factor in the time difference, and whether the special shoes contributed is not certain. The result would be the same even if the special shoes had no effect. In other words, this is an unfair comparison, so doubts remain about the shoe's performance. In statistics, this unfair comparison is called selection bias. Experiments must be an apple-to-apple fair comparison. The most important principle in making a comparison is to ensure it is a fair comparison. But here lies a problem. The company admitted its mistake and has asked you to verify the true effect of these shoes. Your plan is to conduct a valid RCT. To create a fair comparison, you randomly select people, create two groups, and ask them, would you wear these shoes and run a 100-meter sprint at full speed? What happens? Not many people are willing to cooperate. Some might do it for money, but gathering a large sample size would be very costly. RCT are not easy to conduct in the real world. We must think of another way to create a fair comparison. That's where the technique called Propensity Score Matching was born. I mentioned that this is a technique for performing a virtual RCT. Let's take a closer look at this. Data obtained from experiments is called experimental data, and statistically analyzing its results is what an RCT does. On the other hand, there is something called observational data. It is data collected without controlled experiments. It reflects real-world behavior or choices rather than experimental design. While experimental data is obtained by designing and conducting an experiment, observational data is simply obtained by observing people who wear the special shoes and those who don't. There are no homogeneous groups or fair comparisons. PSM deals with observational data. So, how to make a fair comparison? Suppose we have a lot of observational data. If you simply divide this data into a casual shoe group and a special shoe group, there's no guarantee it will be a fair comparison. If people who exercise frequently tend to choose the special shoes, you'll end up with an unfair comparison once again. This is selection bias. On the other hand, if you do random sampling, the special shoes will end up in both groups, making the comparison meaningless. So, how to make a fair comparison? With a large amount of data, it's not surprising to find pairs of similar people by chance. Search through all the data to find the pairs. Perform matching again and again. After gathering pairs of only similar people, if you remove the data that couldn't be paired, you can create two groups of similar individuals. Is this homogeneous and a fair comparison? How to test if it's really homogeneous? Homogeneous means that the average age of both groups is similar, as well as their weight, and exercise habits, and so on. It means that there is no statistically significant difference between them. In other words, if there is no statistically significant difference between the two groups, it indicates that the groups are homogeneous and can be regarded as a sufficiently fair comparison. A group that is homogeneous in all respects except for the type of shoes they wear. Therefore, if there is a significant difference in their 100 meters times, it can be concluded that the special shoes are the cause. So the main idea of PSM is, first, we prepare observational data. So you don't have conduct an experiment. Next, find pairs of very similar people. Then, remove unpaired users. It is possible to artificially create a situation that closely resembles a fair comparison in an RCT. That's why PSM is called a technique for a virtual RCT. From here, let's deep dive into more details. For those familiar with data science, you've probably realized by now that this is a search and matching problem. Randomly select special shoes wearer and search through everyone else. The idea is that you can just search for a person who matches among everyone else to find a perfect match. However, when you actually try to find these matches, you quickly run into another problem. Perfectly identical pairs of people are incredibly rare in the real world. This is the curse of dimensionality problem in machine learning. As the number of variables increases, finding an exact match becomes exponentially more difficult. Can't we alleviate the problem a bit? The first idea is that we might not need perfectly identical users, as long as they are similar in the important aspects. When considering if two users are close, there are many metrics we could use. Some factors are probably not very relevant to running a 100-meter dash. Leg muscle mass is likely an important factor. While differences in blood type may not be very important and could possibly be ignored. By selecting the variables that have a higher priority for matching and focusing on finding matches based on them, we can simplify the problem. Also, we were initially looking for one-to-one pairs. But what we ultimately want are homogeneous groups, so one-to-one pairs aren't strictly necessary. This means that even if we can't find a perfect match for every single individual, it is sufficient as long as the groups are overall similar as a whole. We can still create a sufficiently fair comparison. We can reframe the problem as finding which group an individual is most similar to in tendency. This is easier to solve because we are not looking for a single matching partner, but rather the group that a person fits into based on their overall profile. In PSM, this is achieved using a classification model. First, we take the data and split it into the casual shoes group and the special shoes group. Then, we build a classification model. A logistic regression model is commonly used, but any model will do. This model learns to distinguish what makes someone a typical or atypical member of the special shoes group or casual shoes group. If the special shoes group is dominated by people who exercise a lot, while the casual shoes group is mainly composed of people who don't, the classification model would assign a high score to frequent exercisers and a low score to those who don't. If we then arrange everyone by this model's score and form groups, each group will tend to contain people with similar characteristics. Now, when we have a new person, the model can analyze them and we can determine which group a person should belong to. We do this for every person. Remove any users who couldn't be matched. This leaves us with groups that are similar at the subgroup level. When matching within these stratified groups, it's crucial to balance the proportion of people. If there is a bias in the number of people in each group, we need to adjust the composition of the casual shoes group to have the same proportion. If the overall composition between the groups is not aligned, it won't be a fair comparison. Finally, a fair comparison can be made. The only difference is whether they are wearing the special shoes. So, we can compare their 100-meter dash times. If there's a difference, we can conclude it's due to the effect of the special shoes. Finally, let's understand the remaining details while covering the terminology commonly used in PSM. First, propensity score is a tendency score, showing whether a person is closer to the special shoes camp or the casual shoes camp. It is the output of a binary classification model that contrasts the treatment and control groups, learning their differences and estimating how likely a person belongs to the treatment group. Covariates are the list of features judged important when computing similarity. User similarity is mainly evaluated based on these selected variables, while differences in variables excluded from this list are ignored. Overlap refers to the condition that both the treatment group and the control group share individuals with similar covariates. In other words, for any type of person, there must exist counterparts in both groups. If one group has no comparable individuals, causal effects cannot be reliably estimated. Trimming/discarding is the process of excluding individuals who are too unique to be matched. For example, those with propensity scores that are extremely low or extremely high. By removing such cases, we focus only on people who have comparable counterparts in both groups, which leads to more reliable comparisons. Stratification means dividing users into several groups based on their propensity scores. It is also possible to skip stratification and perform one-to-one matching directly, where each treated user is paired with the most similar control user. Both methods are valid. Stratification improves balance at the group level, while direct one-to-one matching focuses on individual closeness. Caliper. Matching is the process of allowing matches only when the difference in propensity scores between a treated individual and a control individual is small enough, within a preset caliper range. This prevents forced matches with very different counterparts and ensures that only sufficiently similar ai individuals are compared. If you're interested in the details, please leave a comment. We will make another video to explain about various matching techniques. Standardized mean difference/love plot are evaluation metrics or visualization methods to check if PSM was performed correctly. Let's review the whole process while actually running PSM and look at the actual results. Let's actually run PSM using the same data as the previous demonstration, as variables representing user characteristics. There are age, height, weight, weekly training amount, leg muscle, favorite music category, date of birth, and blood type. The type of shoes worn is indicated by the treatment variable. The time for a 100-meter run in those shoes is the time 100-meter second variable. Let's actually check the data. This is observational data, and the casual shoe group and the special shoe group are not homogeneous. If we draw a histogram with the casual shoe group in blue and the special shoe group in red, the age is slightly higher in the casual shoe group. The height is taller in the special shoe group, and there is a clear advantage for the special shoe group in weekly training. In summary, there is a selection bias between these two groups, making it an unfair comparison. Even with a statistical test, it is clear that there is a statistically significant difference between the two groups. All right. So let's execute propensity score matching on this data. First, let's set the treatment variable. Since we are comparing the casual shoe group and the special shoe group, we select treatment as the variable and casual shoes for the control group value. The variable we want to see the effect on by wearing special shoes, the outcome, is time 100 meters seconds. Next, let's set the covariates. Covariates are the list of features judged important when computing similarity. Here, let's define it to consider age, height, weight, weekly training amount, and leg muscle, and to ignore other variables like favorite music category. Set the unnecessary variables as meta-variables. In the PSM model, we will configure the model to calculate the propensity score. As explained earlier, we will select the logistic regression model. For the matching method, select the caliper matching method, and for the matching ratio, select 1-to-1. This means that for every one person in the special shoe group, one person from the casual shoe group will be matched. The caliper value represents the distance between users, and only pairs with a distance below this threshold will be matched. Others will not. Finally, let's configure trimming. We create a homogeneous group by removing users with no overlap from the data. Let's execute and look at the results. The PSM results first show several indicators of the goodness of fit for the generated logistic regression. This is an indicator of how well our classification model captures the characteristics of users in the special shoe and casual shoe groups. As a reference, if the AUC is over 0.6, we can consider the features to be reasonably well captured. Next, let's check how the distribution changed before and after matching. I explained earlier that the control group, the casual shoe group, tends to have people who do not exercise much. This is clearly shown in the blue distribution. We can see that many users are clustered in the lower propensity score range, meaning they tend to have no exercise habits. And after matching, the blue and orange distributions align perfectly, showing that only similar users were matched and unmatched users were excluded. Finally, let's check the love plot and the standardized mean difference. The graph at the top of the screen, made of blue and orange dots, is called a love plot. This graph shows the difference in the distribution of each variable between the treatment group and the control group. When we checked the data earlier, I explained that the age was lower and the weekly training was much higher in the special shoe group. This is represented by the orange dots in the love plot. For the age variable, the orange dot is on the left side, in the negative range, indicating the value was lower for the treatment group. On the other hand, for weekly training, the orange dot is on the right side, in the positive range, indicating the value was higher for the treatment group. The blue dots represent the data after matching. Compared to the orange dots, they are clustered around 0, showing that the difference between the two groups has been significantly reduced by matching. The specific numerical values are listed in the balance metric table. Alright. The output of this widget includes the match data after performing the matching, so let's take a closer look at it. We can see that the distributions of each variable, which previously showed large differences, have been substantially balanced by the matching process, with their curves now overlapping. For example, in weekly training, which had the largest discrepancy, the blue curve for the casual shoes group and the red curve for the special shoes group almost perfectly align. When we run a t-test again and check the p-value, it turns out to be very large, indicating no statistically significant difference between the two groups. In other words, propensity score matching has successfully created a sufficiently fair comparison. Finally, let's examine the outcome. Time 100 meters second. If there is a difference between the two homogeneous groups, we can attribute it directly to the effect of the shoes. Looking at the results, the p-value is smaller than 0.05, and the time 100 meters seconds is lower for the special shoes group. This indicates that wearing special shoes indeed has a causal effect of improving running speed. That's it for demonstration. PSM is a very powerful method, but still, it's not a magic wand. There are two key limitations to keep in mind when using PSM: observed covariates only and the overlap requirement. PSM, like many causal inference methods, can only adjust for variables that are observed. This is its biggest limitation, since unmeasured covariates remain uncontrolled. However, even when the set of variables is not perfect, as long as some relevant covariates are included, matching can still help reduce selection bias between treatment and control groups to a certain extent. PSM requires sufficient overlap in the distribution of propensity scores between treatment and control groups. Without this overlap, matching cannot be performed, and units outside the common support are discarded. This leads to a loss of sample size and limits generalizability. Still, within the overlapping region, PSM can provide a more balanced and reliable comparison.
Learning complete! Now it's your turn. Subscribe for more lessons and experience ai-allye free for 1 month.
Thanks for watching.